All engine running.
Absolute genius.
Get this.
Welcome.
This is the show where we bring you
Science.
What that essentially means is
Discoveries,
advances.
questions,
Research.
technology.
Unbelievable.
Without further ado,
This is The Naked Scientist. Hello, welcome to The Naked Scientist, the programme that brings you the latest breakthroughs in science, technology and medicine. I'm Chris Smith, and this week it's time to put your questions to a big brain panel of people who are going to answer them for you with one of our Q&A shows. We haven't done one of these for a while, so it's great to be back in the saddle. Coming up, can getting your teeth done knock out your hearing? The truth behind truth drugs, or not, and just how much nutrition is there in a human brain? Now that is food for thought.
The Naked Scientist podcast is powered by ukfast.co.uk.
Now, before we start crunching through your questions, let me introduce our panel. First up, we have chemist and author Catherine Harkup. Her latest book is called Super Spy Science, Science, Death and Tech in the World of James Bond, and it focuses on the science and technology involved in that world-famous Super Spy series. She's also written on the subject of poisons that have been used in fictions, such as those featured in Agatha Christie and Shakespeare. And I have to ask you this, obviously, Catherine, what is your number one James Bond gadget?
Oh, I always lean towards the villainous side, and I think my favourite gadget has to be Rosa Kleb's poison-tipped shoe. It's genius.
How does it work?
It's very simple. It's like a button release. You get this very sharp, stabby thing turn up at the end of your shoe. And then, of course, you lace it with something that will kill you, allegedly, in 12 seconds. I doubt there's a poison that will do that, but I'm afraid that henchman who gets kicked with it is as good as dead because they're not helping him.
Something similar happened with ricin on an umbrella, though, didn't it, in real life?
Yes, there was a famous murder in London on Waterloo Bridge that it was allegedly a poison-filled pellet that was fired into a man's thigh, Georgy Markov's thigh, with an umbrella. I'm not sure the umbrella bit is true, but he certainly was poisoned with ricin, and it took him 3 horrible days to die. Not quite the 12 seconds that Spectre manages.
What came first, Ian Fleming doing this with the shoe?
Yes.
Or the umbrella?
No, Ian Fleming got there first. I don't know if anyone was picking up tips, literally. There have always been the idea of poison-tipped weapons. There is nothing new to that. Arrows have been laced with all sorts of nasty since time immemorial, just to kill off various animals for food. So I don't think Fleming can be held responsible in any way for informing on Georgy Markov's death.
One of the things you wrote in the book that I must admit I was amazed by was you were describing, and I've seen, I can't remember exactly which film it was, is where he swims, James Bond swimming underwater using that amazing thing he plugs in his mouth that looks like it's got 2 bottles.
Rebreather.
The rebreather.
Yeah.
And you say in the book that one of the spy services rang up the producers to find out how they did it. Is that true?
That is how the story goes. Apparently, some Secret Service agency had been interested in developing something similar because it has obvious uses in the Secret Services. And so they were fascinated, like they'd cracked the problem that they'd been tackling. And so they got in touch with the producers, and the producers had to confess that this device that you see on screen was actually 2 soda siphon capsules glued together, and the actors were holding their breath.
So it doesn't work after all.
Well, it does now. This is one of those weird things. I do wonder if someone has watched a James Bond film and thought, you know what, that's what the world needs. You can now buy rebreathers. They don't quite work the way they're described in the films. They kind of filter oxygen from the surrounding water, a bit like fish gills, and it will give you some oxygen whilst you're underwater. So I do wonder if Bond has inspired a rather cool gadget.
Are they not huge?
They are bigger than the soda siphon capsules, admittedly, but they're still quite small. It's not like swimming around with a huge tank on your back.
Thanks, Catherine. I'm amazed. I am amazed, and not least that MI5 or whatever watch James Bond films.
Who doesn't?
Well, next up we've got physician and author Jonathan Reisman with us. Jonathan's got a great deal of information to impart about internal organs, everything ranging from inspecting them through to eating them. You can learn about that from his book, which is The Unseen Body, that delves inside our insides and navigates its way through the wonders of our internal systems. Jonathan, you say in your book that the throat is foolishly designed. Why?
As we all know, when things go into the back of the throat, right, they can either be swallowed down the esophagus into the stomach, which is certainly the route that all food and drink and saliva and whatever else we're swallowing should take. There's another route for air to go through the windpipe or trachea into the lungs. And if anything that should be swallowed, such as food or drink or saliva, gets into that airway, one small slip up and you can die or become gravely ill. And yet those two entrances for air and for everything else are right next to each other with just a few millimeters separating them. And every time we swallow, what the material that we're swallowing comes within a hair's breadth of going down the wrong pipe and killing us. So it seems a less than ideal design, though it does work, and we swallow daily for decades without dying, so that's good.
Well, sitting alongside Jonathan, we've got Risa Bagwandin here. Now, Risa's a PhD student. She's actually studying chemical biology at the University of Cape Town. She's focusing on the diagnosis of tuberculosis. It's pretty special, actually, that you're here. So why don't you tell us how you come to be here?
So I met Dr. Chris Smith in Durban, KwaZulu-Natal, South Africa, at a conference called Africa Bioconvention in 2019. It so happened that the conference organizers, along with Chris, presented a Science Communication Fellowship Award, which was awarded to the best science communicator. To get the award, you had to attend a science communication workshop and present in front of a large audience that was attended by ministers. So it was quite.
Well, we thought we needed a good test, so we gave the 3 finalists at the workshop the challenge. They had to stand up at the conference dinner in front of 1,000 people and tell them in 3 minutes what they were working on. And yeah, as Risa says, there was the Minister for Health there and a few other high-level dignitaries.
Yeah, seriously, that takes some doing. Congratulations.
Thank you.
And so they thought she did a jolly good job. And even better, the South African government agreed to pay to send her here. So we're very privileged to have you with us for about 8 weeks.
Yes, that's correct.
And so we thought, given we've got a big chemical brain in the room, we would use it this week. So very warm welcome to Risa all the way from Cape Town. Sitting next to Risa is Peter Haynes. Now, Peter's a mathematician, and you work on climate stuff, right? What are the challenges then, Peter, that people like you are trying to solve? You know, having got weather forecasts that work rather well, what are the unknowns or the less good at bits that we're trying to improve on?
Of course, weather forecasting is only part of the story, right? And one of the challenges we face is thinking about climate change, how things will change in a longer timescale. We're not talking about individual weather events. We're talking about, will the weather be systematically warmer or wetter or colder for a year or a decade or whatever? You know, the fact is that the weather and climate are determined by a whole set of complicated processes. And whilst our models and the way we do those sums, those calculations have improved a lot, they can still be improved further. And also they can take more account of our observations. So we've got many new observations of the atmosphere from satellites and radar, and also, you know, all of these things can be exploited. So it's a sort of continually can do better, must do better kind of topic.
Was it Niels Bohr who said prediction is always difficult, especially when it concerns the future?
Exactly, that's right.
So, anything mathematical and possibly weather-related, that's all coming your way. Let's go back to Jonathan, because we'll put the first question to you, Jonathan. The human body, a mass of interconnected systems and feedback loops. Interestingly, some parts of the body may be more connected than perhaps we realise, because we've got a question here from Liz. Jonathan, she says, is it true that if you have your teeth removed, for instance, dental surgery or otherwise, you can lose your hearing?
That is a fairly well-known phenomenon, but according to my understanding, it is a very, very rare occurrence. You can find reports in the literature about people who lost hearing on one side, partially or completely after a dental procedure, but it's rare enough that if it happens, a dentist is likely to write about it in the medical literature as a rare event.
Do we know what the mechanism might be? Why a person having some kind of dental intervention would go deaf?
Right. So it's actually hotly debated, or not that hotly because it's so rare. But there's some theories that perhaps the adrenaline or epinephrine, which is often in the local anesthetic that's injected into the area of the teeth, might seep through to nearby arteries that feed the hearing mechanism and the nerves feeding the hearing mechanism, and perhaps causing those blood vessels to sort of shrink down or spasm and stop blood flow to the organs, perhaps damaging them through lack of blood flow. There's another theory, actually, that just the sound of the dental equipment, the drills and other things, which can be quite loud and can be quite close to one of your ears, perhaps that sound alone is causing some damage to the hearing organs. Or another theory I came across, perhaps the odd positions you're asked to put your neck into and the how widely you open your jaw and for a prolonged period of time during the procedure perhaps also smushes some blood vessels shut that should be feeding the hearing organ and its neural component.
So one thing Liz probably can't do if she's worried about hearing damage from the drill is to wear earplugs, though, because presumably the vibrations are going to go straight through the bone and into her brain anyway.
True. You'll save damage to the eardrum and the outer parts of the ear, but you can still sustain neural damage to your hearing mechanism. Also, the dentist probably will want to talk to you saying, open wider, stop moving, etc. So you should hear those things.
So probably not a sound and valid reason not to go to the dentist, Liz, on the grounds that you might lose your hearing. Probably unlikely to happen. Catherine, let's come back to you. Catherine, author of Super Spy Science and The World of James Bond. You've also written books on some prominent serums and chemicals that are found in popular culture. One of the common ones in the spy genre is truth serum, mystery substance capable of loosening tongues. But is there such a thing? Does this actually exist, a truth serum? And if so, what is it? How does it work?
I think a lot of people have tried to develop truth serums. It would be extremely useful in questioning if you just know whatever was coming out of someone's mouth was the absolute unadulterated truth. And I think the idea behind a lot of these serums or compounds was it would relax your inhibitions, so you would talk more freely, perhaps a bit like if you're under the influence of alcohol. So in which case you might as well get your interrogee drunk as opposed to giving them sodium pentothal or whatever drug of choice. For a long time, sodium pentothal was used allegedly as a truth serum, basically because it would lower inhibitions. But you could just be talking like a drunk person, just, the first piece of nonsense that comes into your head. So if it's reliably truth or not, I don't know. As far as I know, there's no real truth serum out there, but of course they wouldn't tell me if there was.
You should give them some truth serum then.
Absolutely.
Thank you very much for that one. Peter, let's cross over to you. We've all seen the footage of what's happened to Pakistan. Climate change has had the finger pointed at it for what's happened there with flooding. Other countries as well are seeing very dramatic shifts in weather. And our own country, the UK, we've seen very radical departures from what we regard as normal summer temperatures this year and in recent years. So let's just consider climate change for a minute. One of the things that people often talk about in the context of climate change is what will happen to sea levels. And some of the predictions are only about 30 centimetres of sea level rise in the next 30 years. This question says, why is only 30 centimetres in 30 years such a problem?
I think the key thing here is that whilst sea level rise of a foot doesn't seem to mean very much if you're on the beach or something, right? I mean, we have to think of this in the context of severe extreme events, and any systematic rise in sea level is going to increase the likelihood and the frequency of extreme flooding events. So it's not so much the fact that the average by itself has gone up, it's the fact that those high water events, the times, for example, when tides and the weather kind of reinforce each other, those leading to dangerous levels of water rise are going to become more frequent.
A lot of people also point to Antarctica and the fact that if that melts, that's going to have a really significant impact, and Greenland, of course, because that's ice that's not already in the water, and so it's not floating, and it will therefore directly contribute to a sea level rise, unlike the Arctic, where the ice is already displacing water. So if that melts, well, the water just redistributes, but it doesn't actually mean there's a change in sea level rise.
That's right. So it's the melting of ice on land that's the most will have the most severe implications. And I guess that we've just in the last week or so, one's heard stories, for example, about indications. I think I read a newspaper headline the other day that it was going to be inevitable that the Greenland ice cap was going to be lost to a large extent. But I think another point to think about here is that melting of ice caps isn't the only effect that's going to give sea level rise. Also, just the fact that water expands when you heat it up. is going to make an effect, right? So these things have to be considered together. There will inevitably be sea level rise, whatever happens to the Antarctic ice shelf or Greenland in the next 50 years, simply because of thermal expansion.
Catherine, you were going to say something.
I was going to ask also about once all of this ice disappears from the land surface, do we know what is underneath that's been trapped in? Like, I've heard stories of methane gases from like peat that would be released after thaws and so on. So is there any concern about once the ice is gone, what is left behind?
So Catherine, that's a good point. I mean, so the fact is that certainly there is methane trapped in this sort of seabed. Increase in temperature and melting will potentially release, and methane is a greenhouse gas. It traps radiation near the Earth's surface. It'll increase the overall temperature. There are subtle differences with the way it works from carbon dioxide. But I mean, another effect perhaps that I could mention is this idea of what scientists call albedo, which is reflecting radiation, so that currently and this is relevant actually to mountain glaciers as well as to the Arctic sea ice, that currently where you have ice, you're reflecting radiation back, so you don't get so much heating. As soon as you remove the ice, and actually another effect here is having soot on the ice, for example, which might come from wildfires and things, particularly in mountain areas, that reduces the reflectivity, which means you get more radiation absorbed and more warming. So there are quite a few different sort of feedback effects that might have to be considered as important.
And albedo, quite different from libido. Mustn't muddle those two up.
Indeed.
You're listening to The Naked Scientists with me, Chris Smith, and I'm joined by Jonathan Reisman, Risa Bagwandin, Catherine Harkup and Peter Haines. Still to come, we'll find out how much we really understand about how our memory works, what would happen if the planet were to suddenly stop rotating, and just how nutritious is a human brain. But before that, Risa, let's come to you, because there's a question here from Kate who says, why is glass allegedly not a solid? I thought it was.
Well, when we hold an object made out of glass, we naturally would think that it's a solid material. However, it's not a true solid. For something to be a solid, it needs to have atoms which are ordered and that remain fixed in place. Glass is unique in the sense that it has properties of both liquid and solid. It has atoms that it's ordered in an ordered structure, but these atoms move rather than remaining fixed in position. So the movement of atoms relative to each other is one of the properties that we know that characterizes liquid states.
There's a claim that if you look at old windows, the glass at the bottom of the frame is thicker than at the top, and people say, oh, that's because the glass is a liquid and it's flowed downhill over time. Is that true or false?
Well, that is false. So the reason why the glass is thicker at the bottom is just because of the placement of the glass on the window pane. So normally when you have a thicker surface at the bottom, it'll be more rigid and be able to be fixed in place securely. In fact, quoting the New Scientist, it would take 1 billion years for just a few atoms in a pane of glass to shift at all.
So there you go, Katie. Now you know all about glass, not just something you can see through. Jonathan, let's come over to you. Another one for you. Bruce is saying, I used to work on my parents' farm where we vaccinated cows against brucellosis, which can cause a miscarriage. My wife, and latterly my son's wife, have through their life had problems with miscarriage. Might there be any connection? What do you think?
I think that, acute brucellosis infection, that is infection with bacteria in the genus Brucella, is known to cause miscarriage, especially in animals. It's one of the most common causes, infectious causes of miscarriage. And it does seem to also, with acute infection, like acute infection with fever, does cause a miscarriage in a high number of women. I saw some studies that have just under 50% of women with acute brucellosis may suffer a miscarriage. I think that outside the context of an acute infection with fever, that's harder to say. There are some chronic brucellosis infections that can be smoldering over years. I don't think it's as clear that they cause miscarriage at all. So I doubt if there's any symptoms of any kind or there's any acute infection with fever. Probably not related to those miscarriages that seem to run in the family. There are many other things that can cause miscarriage for it to run in families, such as clotting disorders. But I doubt it's chronic brucellosis as the cause.
So some reassurance for Bruce. And Jonathan, thank you for clearing up Bruce's problem anyway. Well, now it's that part of the show where we put our experts' knowledge to the test. It is quiz time. You are competing for a prize beyond price. It is the Naked Scientist Big Brain of the Month award. It's invaluable. People who've won this have gone to very, very great places. And I mean that. Team 1 is going to be Catherine and Jonathan. Team 2, giving them a run for their money, Risa and Peter. You are actively encouraged to confer. So do share your thoughts and cogitations with yourselves and with the audience. Round 1 is called On This Day in History. So, Catherine and Jonathan, question 1. September the 15th, a date that echoes through history. On this day, the 15th of September, 187 years ago, Charles Darwin first landed in the Galapagos Islands, would you believe? He was best known for having his big beard and bad handwriting, as well as having some pretty important theories to impart. He was, though, also an avid collector of which group of invertebrates? I've got 3 options for you. A, ants, B, beetles, or C, butterflies. So Jonathan and Catherine, Darwin had a penchant for collecting what group of invertebrates?
Are the interesting beetles in and about his home, or was he collecting them in the Galapagos? I don't know what the beetle population of the UK is and how exciting it is and whether it's worthy of collecting.
Jonathan?
I do know that beetle diversity across the world is quite staggering and surprising, so that I might vouch for that answer.
It's a good choice. It is answer B, beetles. Darwin was a huge collector of beetles, and his collection of thousands of them from the Beagle Voyage is in the Natural History Museum in London.
Yes.
Well done. +1 to Team 1 so far. I shall mark you up as 1 point. Question 2. This is going to Risa and Peter. September the 15th, 1928 is also an important date because it's the date on which Alexander Fleming discovered the effect of a pretty important mould that turned out to be world-changing. But how many lives do we estimate penicillin that came from that mould has since saved since it was rolled out in 1942? So Risa and Peter, penicillin, how many lives saved since? A, 20 million, B, 200 million, C, 2 billion lives saved. What do you think?
Well, if we take the approximation, there's 6 billion people on the planet in a lifetime.
Well, your comment about how many people on the planet has made me think actually 2 billion is too many.
Mm-hmm.
So perhaps we go for 200 million.
I'm thinking 200 million.
Yeah, okay, let's go for that.
Okay.
It's a good one to go for. It is 200 million because that's about 2.5 million lives a year that get saved from diseases like meningitis and pneumonia. So it is 1 point apiece, level pegging after round 1. Back to our team number 1, Catherine and Jonathan. Your question in round 2, which is close family and neighbours. The first animal to orbit the Earth was A, a mouse, B, a dog, or C, a pig. What do you think?
Oh, I'm pretty sure both a mouse and a dog have been sent into space. I'm not sure a pig has. I missed that particular news item if it was sent into space. But I don't know whether a mouse or a dog went first.
I do know that the Russians sent up a dog named Laika.
Yeah, I don't know if they did any experiments before with smaller animals. I imagine, the weight would have been an advantage when launching something into space. But I'm happy to go with the dog because I've definitely heard of Laika and going into space.
Going with that, Jonathan?
Sure, let's go with Laika.
It's a good one to go with. You're quite right. Yep, Laika was the first animal in orbit. It was on Sputnik 2, November 1957. She was part of the Soviet space dog program. And the half-a-ton Sputnik 2 satellite, unfortunately, didn't have a very good life support system on it, though. So she didn't live very long, but she did live long enough to be the first animal to orbit the Earth. And then she burned up in 1958 when the satellite was returned to Earth. Well done. It's a point for you. Over to Team 2. This is Peter and Risa. And we're going to stay in space with this one. Our galaxy is the Milky Way. It's one of billions of galaxies that's spread out across the universe. But who is our nearest neighbouring galaxy? Who's our nearest neighbouring galaxy? Is it the Andromeda Galaxy, Canis Major, or the Tadpole Galaxy?
I have no idea.
That's right.
This is something that I've not paid much attention to.
There was a nice exhibit in Cambridge a few weeks ago of planets and along the river, but unfortunately they didn't get to galaxies, right? Because if they put galaxies in it, I might have known the answer. I mean, tadpole seems very unlikely to me, but
I agree to have tadpoles.
What was the
as
first one?
Andromeda, Canis Major, or the Tadpole Galaxy?
Go for the middle one.
Is that what we're going for? We'll just go with the one in the middle, like filling in the MC multiple question sheets.
Perhaps just go for tadpole because it's unlikely.
Don't have to hurry.
Okay.
What do you think? What are you going to go for?
We'll go with B since that's our default now.
Okay, you're going for your default answer, and it's the right thing to do. It is Canis Major. Now, the Tadpole Galaxy, does it really exist because it looks like a tadpole? It's 420 million light years away. That's a long way off. Andromeda, 2.5 million light years away. That was thought to be our nearest neighbour until very recently, actually. But Canis Major now has the crown. It's actually 1,000 times closer than Andromeda, 25,000 light years away. It's our nearest galactic neighbour. It is still a long way off, though, because even our fastest spacecraft, which is the Parker Solar Probe, would take a mere 39 million years to get there. So that's a point for you, too. So level pegging at the end of round 2. We might be in tiebreaker territory. Let's find out. Round 3 is called Back to School, and it's GCSE time. So schools have all gone back recently. The GCSE results, which we sit here in the UK, are not far in the past, so time to see how you would fare at GCSE. We want to know, Team 1, this is Catherine and Jonathan, what is hotter? A, the boiling point of iron, B, a lightning bolt, or C, the surface of the sun? What's hotter?
So for me, I think it's between the surface of the sun and a lightning bolt. I'm going to discount iron because I think that's, although boiling point, that's, I don't know.
I was crafty there, wasn't I?
That was crafty.
Yeah.
See, if you said melting point, I'd have dismissed it out of hand, but boiling point?
Yeah, you see, I knew you were coming on the programme and I thought, chemist, she's going to know that I'm going to be crafty.
It's almost like you planned it.
I did. Jonathan, any thoughts?
I agree, Catherine, that I'm a little perplexed because they're all certainly very hot. Could anything on Earth be hotter than the surface of the sun, I wonder?
I think it's one of those deceptive questions where the surface of the sun, everyone imagines it's going to be super, super hot, but actually it's not as hot as lots of other things. For example, a lightning bolt. That's my gut reaction is a lightning bolt.
Going for that one?
I'll back you up on that one, Catherine.
Oh, bless you.
It's a good choice. It is a lightning bolt. Let me tell you about iron. You were quite right with iron. 1,500 degrees C is the melting point, give or take. The boiling point, craftily, 2,800 C. I did that on purpose. The sun's surface, 5,000 degrees C. Lightning superheats the air around it to a sizzling 30,000 degrees C, so it's about 6 times hotter than the surface of the sun. Well done. So you get a point for that one as well. You've got to get this one right, Team 2, Risa and Peter, because at the moment they've got a full house. We're over to biology for you two, and we want to know how many bones are there in a great white shark? Is it 0, 536, or 2,804? 0, 536, or 2,804 in your average great white?
Any thoughts?
Well, the non-biologists have this vague idea that sharks don't have bones. They have some other kind of solid material in them, right? But I could be distracted because Catherine has just made a gesture at me which suggested that what the answer was.
She's trying to put the opposition on.
I'm trying to make it a fair competition. I want the best out of everyone.
I'm going to go with Peter, yeah.
Which is
0.
Yeah.
Peter's going 0. Answer A. You're breaking with your tradition. You went B every time.
Yeah, well, I mean, that was a tough
I
decision.
can't tempt you with 536.
No.
It's a good choice because it's not right. A is the correct answer. Sharks are cartilaginous fish, so they are not bony. There are no bones in a great white shark. Well done. So that means it's tiebreaker time because you have all got 100% so far. So the tiebreaker is, how are your Nobel Prizes? How are you on Nobels? Are you good on Nobels? We'll find out. We want to know what year the Nobel Prizes were first awarded. Jonathan's down the line, so I'm going to ask him to start. So, Jonathan, what year do you think the Nobels were first answered? You're not allowed to quickly flick out your phone and go looking at this either.
No, of course not. I may be close or very, very wrong. I'll go with 1938.
Okay, 1938. Catherine, any thoughts?
I'm going to go much earlier than that because I think it's 1900 something. I'm going to guess 1904.
Catherine goes 1904. Peter?
I'd go a bit earlier. I'd go for 1895.
1895. Risa?
I have to admit I know this one. So I've been following the Nobel Prize winners for quite some time. So the first Nobel Prize was awarded in 1901.
And you're right. So our Naked Scientist Big Brain of the Week award goes to, this week, Risa and Peter. Very well done. I think we should give them a round of applause for that. Very well done.
The Naked Scientists podcast is produced in association with Spitfire, cost-effective voice, internet and IP engineering services for UK businesses. Find out how Spitfire can empower your company at spitfire.co.uk.
Music in the programme is sponsored by Epidemic Sound, perfect music for audio and video productions.
You're listening to the Naked Scientists Q&A show. I'm Chris Smith, and with me are Jonathan Reisman, Risa Bhagwandin, Catherine Harkup and Peter Haynes. Coming up next, what is hard enough to cut a diamond? Is methane really worse for the environment than carbon dioxide? And we'll be finding out how long you could survive if you were to chow down on a human brain. But let's go over to Catherine now and back to the spy films for you, Catherine. We talked briefly about the story of being prodded with umbrellas and so on in London to poison people. Is this really practical, though? Could you lace an everyday object with something toxic? We've heard about door handles and Novichok, so that obviously works, but that's rather outside the scope of that. Is it practical to lace everyday objects with something toxic?
People have certainly tried in the past to, there's all sorts of stories of like the king's gloves or the king's saddle being laced with poisons that would bump off the monarch so that someone else could take their place. How effective they would be, I'm not sure. Your skin is a very effective barrier to the rest of your body. So there are relatively few compounds that will make it through into your bloodstream and then actually cause damage to the system as a whole. But that's not to say that there are none, as Novichok has proved. Today, I don't think you should worry about it too much because you can't make Novichok in your back garden. You do need access to specialist chemicals, and they are monitored as to who buys them and what combinations are bought together. So actually making it practically for your home poisoner, very difficult.
It's what's called a binary toxin, isn't it? You have to bring two different bits together to make it work.
There are certainly binary toxins. I don't know if Novichok is one of them, but certainly it has been suggested that the compound that was used to kill Kim Jong-nam, the half-brother of Kim Jong-il, there were two women who were involved. One sprayed something in the man's face and the other one wiped a cloth over his face. Each would have had separate chemicals and they would have combined on his face to produce a toxin, which means that the two women involved should be relatively unaffected, as would be everyone else around them. But the individual with both has obviously very severe effects.
I didn't know that. I'm fascinated. Thanks very much. Back to you, Peter. When ice melts, it's adding fresh water to the ocean. So does this mean that progressively, as we go through climate change and so on, that the salinity of the world's oceans will change, do we think?
As always, there's a kind of slightly complicated answer, right? Because actually, what we expect is that some parts of the ocean will get more saline and some parts will get fresher. I mean, the fact is that climate change is associated not only with more melting of ice, but also more evaporation. So where you've got water flowing out from melting ice sheets, the ocean will become fresher. Where you've got more evaporation, like in the Mediterranean, for example, then the water will get saltier. And of course, what you see, if you go to some point in the ocean, what you see is some subtle combination of all of those processes that are taking place over the globe. And then the effects are brought by the circulation to the place you're looking. Okay.
When you add fresh water to salt water, because they're different densities, that can have effects, can't it? Because I've seen quite a lot of speculation about the impact of the Gulf Stream and the melting of the Arctic, pushing that backwards and potentially making Britain colder through global warming because we lose that heat source that comes up the west coast.
Exactly, that's right. At the moment, you get something called convection, where, if you like, heavy water, dense water sinks in the northern Atlantic, sort of Arctic Ocean. And, that happens in part because of salinity, which adds to the density. And if you were to kind of flood the top of the ocean with fresher water, then that combination of temperature and salinity that determines density may no longer give to sinking, right? And some part of the kind of circulation system of the Atlantic is driven by this process. And so there would be potentially a change. I think the jury is still out on how likely it is to happen. Or another question would be, when would it happen? There's a lot of discussion about tipping points. I mean, that's another favourite idea in climate science at the moment. And if you look at the kind of list of tipping points, this is one which is sort of somewhat lower down the list. It's an effect which could happen, obviously would be potentially serious, but it's not one of the ones that is seen as sort of most likely and most imminent.
Thank you, Peter. Jonathan, back to you. We've heard from Dan, who's written to say, I've heard about the stomach being a second brain or there being a gut-brain connection. Is this true? And if so, what would be the point of such a second brain?
Great question. There is an entire nervous system of the gut called the enteric nervous system. And in some ways, it does operate semi-autonomously from our primary nervous system, the brain, spinal cord, nerves coming from there. So that nervous system of the gut, the enteric nervous system, helps control the gut's motility, helps push food forward through peristalsis, helps impact the blood flow to various parts of the tract, helps regulate also the endocrine function of the alimentary canal. There's quite a lot of hormones that are secreted to impact its function and timing and things like that. And there's also immune function in the gut itself, since the external world through the food that we eat presents a lot of microbes that can hurt us. So there's a good, strong immune system also regulated by this enteric nervous system. Our central nervous system does impact and regulate the enteric nervous system mainly through the vagus nerve, which comes down from the brainstem and impacts alimentary canal function. But even if you sever that nerve, even if you completely separate the enteric nervous system from the body's primary nervous system, it continues to function largely on its own. Not completely, but mostly on its own. It seems like a good backup system to have that can function mostly on its own and keep you alive despite that severing that connection.
So when people talk about gut instinct, they're not wrong.
They're not wrong, though. That's one of the anatomical metaphors that we use throughout our language, but it does make some sense.
Peter, let's come to you. Phoebe's written in and says, I have read that methane is a worse greenhouse gas than carbon dioxide. Why is that? Is it something to do with the molecular structure of methane?
Okay, so the common feature of these two gases is that the molecules, there's sort of several atoms, if you like. There's 3 atoms of carbon dioxide, there are 5 in methane, and that means that they can vibrate frequencies which are relevant to absorbing infrared radiation, absorbing heat radiation. Okay, so they can both absorb radiation and also re-emit it. It's those sorts of differences determine how effective the greenhouse gas is. There are also other effects, like, for example, what are called sort of window effects, right? That if something absorbs in a wavelength which other molecules don't absorb in, then it can actually, its overall effect can be more powerful than you would have thought. So these things can kind of be weighed against each other.
So if I've got a whole heap of methane, is my best option then to set fire to it? Because it will be better for the environment to do that than to leave it as methane in the atmosphere?
I think I would say almost certainly not, right? But I mean, there's something which we talk about as a lifetime. If I put a molecule of carbon dioxide in the atmosphere, then it stays in the atmosphere for hundreds or possibly thousands of years until it's probably absorbed by sort of geological processes, actually. If I put methane into the atmosphere, there are chemical processes that break it down. So all of those things have to be taken into account when you're sort of comparing the merits or demerits of different molecules.
So short term, yes. Long term, probably not, then.
That's right. Yeah.
Thank you for that. Let's go back to Jonathan and memories, something which some of us struggle with. Some of us have very good memories. But we've got some questions on this, Jonathan, so perhaps you can help us out. David says, what exactly is the memory state? How does the brain store memories? And how is that a biological process? What does it do?
Well, good to always start out by pointing out that our knowledge is very incomplete on the science of memory, as with most things in the brain. I think it's safe to say that there's no equivalent of the brain has no equivalent of a gallbladder that stores bile or a bladder that stores urine. There's no sack of memories up there that can be located upon dissecting the brain. But I think some things we do know about memory and how it's stored is that the brain, like many other aspects of its function, including consciousness and subjective experience, is not all in one location, but rather spread out in a number of parts of the brain. It's quite a geographic and distributed process. But we certainly know that different aspects of memory are operated upon in certain parts of the brain. For instance, kind of on the inside of both of your ears and the temporal lobe is an important part of how short-term memories are made into long-term memories in structures such as the hippocampus that are in there. But we also know that, for instance, if you have a particular memory, the emotion associated with that memory is stored in another part called the amygdala, another part of deep in the brain. So that's different than the actual facts of the memory, the place, the person. Even, let's say, someone's face, you remember their face. The long-term memory of that image is it seems stored in the visual cortex, so in the back part of the brain, in the occipital lobe, where other facts about that memory or emotion tied to that face will be stored in other parts of the brain. So it's all very broken down and certainly complex. And how a neuron actually stores memory, I don't believe is really well known at this point.
Thank you very much for that one. Let's come back to you, Catherine, and we end up invoking James Bond again, because this question's about diamonds. Is that one of your favourite films, Diamonds Are Forever?
Oh, it is good fun, yes. There's lots of silliness in that film, but it's very enjoyable, entertaining silliness.
Well, let me tell you about this question, which says, we know diamonds are made up solely of carbon, so are lots of other things. So what's special about the arrangement of the carbon in diamond that makes it really strong compared to other things like graphite that are not?
Diamonds are very special. It is a unique combination of carbon atoms in that every carbon atom within a diamond is connected to 4 others, and those 4 are connected to 4 others. So a single diamond on a ring, that is, in theory, 1 molecule of carbon, which is quite an extraordinary thought. You don't normally expect to see a molecule of something, but that's the kind of scale it's operating on. And all of this interconnectedness means that it is very difficult to chip off a bit of carbon, which gives it its strength. But also this arrangement also gives it its beautiful clarity and its luster and reflects light. So a lot of what we attribute and what we love about diamonds is their visual impact and their cultural associations rather than their physical properties.
Where do they come from?
They come from very, very deep within the earth. So they were formed many millions of years ago. And the only reason they ever make it to the surface was if many hundreds of thousands of years ago, a volcano happened to push through this particular bed of rocks. And so if the temperature wasn't too high, the pressure wasn't too crazy and in flux as it shifted right up to the surface of the earth that it destroyed the diamonds, then you might find diamond deposits on the surface of the earth. So they come from deep, deep within the earth's surface. They're very, very old. But of course, you could just make some in the lab these days.
One thing I've always wondered, and this sounds like a bit of a daft question, but it's a genuine, straight-up question. If diamonds are the hardest thing, what do you cut them with?
Other diamonds. So it's a real skill, cutting diamonds. The people that do it, they are artists, and they train for a long time. And so you have to find, because the crystals that you dig out the ground, they're also not perfect. These are natural substances. They will have flaws. They will have cracks in them that you can take advantage of, but also you want to avoid in the finished product. So spotting where all of those flaws are that you can use and manipulate and shape and cut into another diamond using a diamond, it's all very difficult and lots of planning goes into it because huge amounts of money can be lost if you make the wrong cut.
I can imagine. That's fascinating. Thank you for that, Peter.
Well, I'm interested in this idea of diamonds, right? So do you get anything like diamonds but made of other elements? You've said that it's like a diamond is like a single large molecule of carbon. Do you find other single large molecules of other elements?
You can get single crystals of metals. that are highly, highly organised and grown in specific ways. They use it a lot for engineering purposes because in theory there are no flaws within this metal, so there's no source of cracks and they're very hard wearing.
Are they called metallic glasses? Because I did meet a materials scientist who told me that they are great for golf clubs.
Wow,
apparently.
they must be I've heard them being used in like jet engines, for the blades of jet engines, because obviously they're under an awful lot of pressure and they have a lot thrown at them. So yes, they won't look as beautiful and clear as diamonds, simply because they're metals and the electronic structure within is very different. But yes, in theory, you can have not specific diamond structures, but highly organised, massive single molecules of other elements.
Okay, thank you.
Well, Catherine, thank you very much for your 24-carat insight to that one. You're listening to a special edition of The Naked Scientists. It's a Q&A show. I'm Chris Smith, and with me answering those questions are Jonathan Reisman, Risa Bhagwandin, Catherine Harkup and Peter Haynes. Still to come in the programme, is there space dust in raindrops? Why do James Bond films love lasers? And what would happen if the planet suddenly stopped rotating? Before that, though, Jonathan, this question's for you. I think it must have been sent in by Hannibal Lecter, actually. Are you ready for this? It says, how much nutrition would you get from eating a human brain?
Well, besides the legal and ethical questions about eating another human's brain, it's a very nutritious and very high-calorie meal. The average a human brain is about 3 pounds, or about 1.3 or so kilograms, and 60% of it is fat. So myelin, which is the substance that sort of insulates all the nerves, if the nerves were wires, myelin would be the sort of rubber coating on the outside. So a lot of that fat would provide a lot of calories, probably enough calories to last you several days, if you had only one human brain to subsist on. There's also protein, various kinds of minerals, some B vitamins as well. And I don't know if the person asked for a recipe when they submitted this question, but I would go with the traditional brain sandwich preparation method common in the city of St. Louis, which is to slice the brain, dip it in egg, spice it, and then deep fry it before putting it on a rye bread with a hot mustard for the sandwich.
Delicious. I might ask the rest of the panel for their brain-related recipes. Catherine?
I have a question. I remember seeing a sign once many years ago that said smart cannibals don't eat brains because of the diseases that can be transmitted and accumulate within the species because of it. Is that true?
Yes, the most famous example is diseases of the prion or prion form. There's a disease called Kuru, historically common in Papua New Guinea, where cannibalism was more common, perhaps in ancient times than it is now. But there was ritual eating of people's brains after death, and this prion disease, Kuru, was transmitted from person to person. There's also, mad cow disease or bovine spongiform encephalopathy, which can be transmitted, though I'm not totally clear how common it is for it to be transmitted to humans. But eating the nervous tissue or the brain of infected animals does put you at risk. I think the risk of contracting any of those prion diseases, including mad cow or chronic wasting disease, which is very common in white-tailed deer here in the U.S., the transmissibility to humans is not well documented. But certainly in the case of Kuru, which every medical student in the world knows about because it's such a unique instance, there's definitely a risk there.
Thank you for that. Food for thought, if I may. Let's come to you, Peter, because I've got this question here from Katie, who says, I've heard that there is a drop of space dust in every raindrop. Is that true? If so, how does it get there? And is it harmful?
So I think the simple answer is there is not a piece of space dust in every raindrop, but there is dust in every raindrop because the formation of drops is basically helped significantly by solid particles, and it's much easier, if you like, for water to condense and form a drop or ice also on a particle than it is simply without that. So there's an element of truth there. There's no space, but there's certainly dust. But,
we interviewed the guys on this show. It was about 20 years ago, but they flew collectors through clouds to see what was living in clouds, and they were very surprised to find lots of bacteria in the clouds, including bacteria that seem to make holes in trees, and so that the bacteria get blown up off the tree into the cloud. They make rainfall in the cloud by doing exactly what you say, with making water droplets form around themselves, and then they rain down on a new plant that they can infest and infect. They found that, but they also said there was dandruff. They found evidence for dandruff in clouds, doing again the job that you're
actually, that's
saying.
consistent with what I said, that any dust is good dust, right?
And it wasn't just human dandruff. I mean, there's a lot of animal dandruff as well, but it was just intriguing to me to think that, you shake a cloud and you get some it's not just snow that comes out, there's some other white flaky stuff in there, and it might be some old dandruff. Can you help this person out, though, Peter, as well? Because this person's wondering how we detect what's in the atmosphere, not of our own planet, but other planets around other stars. So if we look out into space, and we're now at the stage where we've got telescopes powerful enough to see not just distant stars, but planets around them, scientists are reporting what's in the atmospheres of those planets. How do they know?
Well, I mean, the first thing to say is it's actually, to me, as a bit of an old guy, this is kind of amazing, right? Because it's only sort of 30 years ago, probably less, that we saw the first planet outside the solar system. So the idea that now we can actually start to say what's in the atmosphere is actually pretty amazing. But we're seeing this basically through radiation. That if you look at the spectrum of radiation, the distribution of radiation over different wavelengths that you see, coming reflected from a planet, or a bit, perhaps the radiation has come from a star near the planet, then through the planet's atmosphere, and then to us. Then by looking at this spectrum, you can deduce something about the chemical species that are in the atmosphere.
Can you help this person out? Because back to the James Bond theme, lasers feature prominently, don't they? And you do dwell on this a lot in the book, where you sort of say they needed something, a death ray or something that would be sufficiently wow people out, but also grounded in truth. Is that really why they went for lasers, or was there another reason why that has become so popular in these movies?
I think lasers, they are almost synonymous with spy movies. Everything's better with a laser attached, surely. But in 1964 or 63, whenever they were filming Goldfinger, the original book had a buzzsaw that was threatening the life of James Bond, and that was a bit hackneyed, I think, even when Ian Fleming wrote about it. So they wanted to update it, and in the 1960s, lasers were a new thing. They are now common, everyday objects. Lasers are everywhere. But in 1964, they needed explanation because the majority of the audience had never seen one before. They understood the concept of a death ray. That's kind of a common trope in science fiction, but a laser specifically. So they gave dialogue to Auric Goldfinger to say it is a concentrated beam of light that can melt through metal and it can project a spot on the moon, which is absolutely true. And of course, to show it on screen, you have this brilliant red line heading towards Sean Connery's nether regions, which of course you wouldn't see, because metal cutting lasers are invisible, but having an invisible beam travelling up a metal sheet makes no sense in a cinematic situation. So of course you put a red light on it. So the whole concept of red lights and laser beams, I think it is a wonderful combination of ultra-modern, cutting-edge science, literally, but also a trope that an audience understands. And so it symbolises the old and the new very, very nicely throughout the James Bond franchise.
I want to finish by, just before we ask Peter the last question, by asking you, because I've got a theory on what I think your favourite James Bond movie is.
Okay.
What is your favourite James Bond movie?
I mean, it varies depending on my mood, but if it comes on TV, the one that I'll probably sit through till the end, although I've watched them all many, many times, there's a lot wrong with it, but I will always sit through to the end of Live and Let Die.
Why?
Best ending of a Bond film. Baron Samedi is awesome.
I love the music. I do share your enthusiasm. I think the music in that film is superb.
The best soundtrack, yes.
But The Spy Who Loved Me is also, I think, excellent. And I was torn. I had in my mind that it was going to be Live or Let Die or Spy Who Loved Me. That it was going to be your choice.
Okay. No, it would definitely be Live or Let Die.
Peter, got a favourite?
Well, yeah, I like Live and Let Die, yeah. But I must confess there's a bunch of Bond movies that I haven't yet watched. But hey, I've got those ahead of me, so that's good.
Jonathan, got a favourite Bond movie?
This may come as a shock, but I've actually never seen a single James Bond movie, I'm sorry to say.
Don't worry, Jonathan, you're in quite good company, because on this programme we had the author of The Martian, as in what became the Matt Damon Hollywood blockbuster, and there was a very important professor from a very high-profile university in the States who said, sorry, I haven't watched it. And the author said, I don't like him, but I do like her, to one of the other guests on the programme. So you're in good company. You know, a lot of people haven't seen all these films. Anyway, Risa, a favourite Bond movie?
I'm going to be with Peter here. I haven't seen much. Or if it was on TV, I didn't watch it from the beginning all the way to the end.
Well, this sounds like the story of a good Bond movie, this question, Peter, so it's going to come to you to answer it. And that is, this person's wondering, what would happen to Earth if the planet suddenly stopped rotating? What would the atmosphere do? There must be a maths equation for that.
Well, yeah, there are maths equations for almost anything interesting, right? But I mean, actually, this is interesting. So there are many ways to answer this question, right? You know, if the Earth suddenly stopped rotating, well, I mean, a whole bunch of things would probably sort of fly off, right? In some ways, it's almost more interesting to think about if it slowly stopped rotating. But perhaps, you know, I may be misinterpreting the question, because there are planets that don't rotate. Many of the exoplanets that have been detected are what's called locked. They're tidally locked, so the same side of the planet is facing the star, right? So there's obviously a very extreme difference between the sunny side, so to speak, and the not so sunny side. I mean, one effect of the Earth stopping rotating would be that we wouldn't, you know, the day would become much longer, right? Because
well, that is sort of happening, isn't it? Because Earth's rotation is slowing down.
Indeed
because
it is,
we are losing some energy to the moon. Because there was that story earlier this year saying it's been slowing down and we have to keep adding the odd second here and there to keep track of time, but then suddenly it speeded up again, and we actually covered the fact that the Earth was about a millisecond per day less long than it should have been in July.
Well, there's a whole bunch of interesting things there, right, which actually another thing that affects, on short time scales, another thing that affects the rotation rate of the Earth is actually the weather patterns, so to speak. There's this thing called angular momentum, amount of spin, and you can exchange angular momentum between the atmosphere and the solid Earth. So fluctuations on short time scales can be a result of that. I mean, if in an atmosphere that wasn't rotating, another answer would be that actually what we atmospheric scientists think of as the tropics would sort of expand, right? Which isn't to say that everything would become warmer, but we'd sort of have tropical weather over a much broader proportion of the Earth's surface, because the rotation of the Earth is very important in determining how weather systems work, right? And if you go to the tropics, then actually it turns out the rotation is not so important. So the tropics would expand if the Earth stopped rotating.
So can I ask, in true Bond villain fashion, will global warming, if I could speed it up, will that also speed up the rotation of the Earth as we get more violent weather systems going on?
I think these are more fluctuations than systematic effects, right?
Damn it, I almost had the plot of the next film.
Yeah, you could imagine dangerous variability in the rotation of the Earth, right? Is it slowing down? Is it speeding up, right? But that's stretching things a bit far. But hey, if the people writing this Bond movie want some new science to put in...
If the broccolis are listening, I thought of it first.
Yep.
Your name will go on the credits, Catherine.
Thank you.
Well, there we must leave it. And I must say a very big thank you to super spy science author Catherine Harkup, to Risa Bagwandin, unseen body author Jonathan Reisman, and Peter Haynes. Thank you all very much for joining us for this episode of The Naked Scientists. We're back at the same time next week when you can find out about science from Trieste, the city of science. We're off to the Science Festival and then we'll talk to the populace to find out about the amazing research that's going on there. The Naked Scientist comes to you from the University of Cambridge's Institute of Continuing Education. It's supported by Rolls-Royce. I'm Chris Smith. Until next time, thanks for listening and goodbye.